Hello everyone, I'm Dmitrii Kuzmenkov and I'm happy to be here today to talk about Retrieval-Augmented Generation, or RAG, as we'll call it throughout this presentation. We'll explore how this technology is revolutionizing the way we interact with AI systems and how it can help us to get smarter, more accurate answers. Let's dive in. Today's agenda covers four main sections. First, we'll start with the fundamentals, what RAG is exactly and what it matters in today's AI landscape. Then we'll explore the evolution of RAG systems from simple implementations to more sophisticated graph-based approaches. Third, we'll dig into practical optimization techniques that can significantly improve your RAG implementations. And finally, I'll share you our journey at Mantocore Search, where we've been implementing and refining RAG for smart web search on our website. By the end of this talk, you should have a solid understanding of RAG systems and some practical insights to apply in your own projects. Let's get started. So, what exactly is RAG? At its core, Retrieval-Augmented Generation combines two powerful capabilities: retrieval, finding relevant information from a knowledge base, and generation, creating coherent responses based on retrieved information. RAG enhances LLM outputs by grounding them in accurate, up-to-date external knowledge. So on one side, we have large language models, or LLMs, like GPT-4, Claude, or Llama. These models are incredible, generating coherent, contextually appropriate text, but they have limitations. When we use LLMs alone, we run into several challenges. First, they have limited context windows. They can only process a certain amount of text at once. Second, they only know what they were trained on, which means their knowledge has a cutoff date and they don't have access to your specific information. And third, if you try to overcome these limitations by stuffing large amounts of information into the prompt, you'll quickly rack up token costs and face performance issues. This is where RAG comes to the rescue. RAG systems capture the semantic meaning of your data and store it as vectors. Retrieve only the most relevant information when needed. Use various techniques to ensure the right information is found. And ultimately, make the LLM more knowledgeable about your specific domain or data. Think of it as giving the LLM the ability of look things up before answering, just like we do when we are not sure about something. So let's break down the core components of a RAG system. First, knowledge preparation. Actually, this involves collecting, cleaning, and organizing your data. Second, vectorization and storage. Converting your text into numerical representations, vectors, that capture semantic meanings and storing them efficiently. Third, retrieval and re-ranking. Finding the most relevant information based on your user query and potentially refining those results. Prompt assembly, combining the retrieved information with the user's query in a way the LLM can use effectively. Generation, having the LLM create a response based on a assembled prompt. And sixth, optionally, post-processing, refine the generated response, adding citations and other enhancements. Here's how it works. So let's look at flow. A user asks a question. Optionally, we can split it into multiple queries or adjust it with LLM. We embed this question into a vector, retrieve the most relevant documents, re-rank them if needed, assemble a prompt with the context, have the LLM generate a response, and optionally post-process that response before showing it to the user. This approach grounds the LLM's responses in your specific data, making them more accurate and relevant. Now that we understand what RAG is, let's look at how it has evolved over time. So, RAG is relatively new, but has developed rapidly. In 2020, Lewis and others published the first formal RAG paper establishing the fundamentation concept. By 2021, early adopters were already applying RAG to chatbots and basic search functions. 2022 saw significant improvements with cross-encoder reactors boosting relevance by around 40% and dense passage retrieval, making search more intelligent through contrastive training. In 2023, major cloud providers like AWS, Amazon, Azure, and Google Cloud started offering RAG as a service, and plug-and-play RAG systems made deployment much easier for companies and enterprises. Looking ahead to 2025 and 2024 before, we are seeing the emergence of self-optimizing RAG systems that use feedback to automatically tune themselves, and more sophisticated approaches like GraphRAG that understands relationships also between entities. The pace of innovation here is remarkable, and we just get starting. So let's explore the different types of RAG implementations that have emerged. First, we have simple RAG. The basic implementation where an LLM retrieves relevant documents from a database to ground these responses. This works well for straightforward use cases like fax systems. Next is simple RAG with memory using the basic approach by storing information from previous interactions. This is particularly effective for continuous conversations where context builds over time, like a customer support scenarios. This means each turn isn't just processing the current user input in isolation, but rather making retrieval queries that takes into account the accumulated context. Look at this diagram. This diagram shows the architecture of a simple RAG system. As you can see, we can have the document collection on the left, which go through embedding and indexing processes. When a user query comes in, it's embedded. Relevant documents are retrieved, and this context is combined with the query to generate a final response. Even the basic architecture is powerful, but let's look at more advanced approaches. Branch RAG intelligently decides which specific data sources to query based on the input rather than searching all sources. This is perfect for specialized domain like legal research, where different types of information might be stored in different repositories. Hide or hypothetical document embedding creates an embedded representation of what an ideal document would look like before retrieval. It's like saying, if the perfect answer existed, what would it contain? And then searching for documents that match that ideal. Adaptive RAG dynamically adjusts its retrieval strategy based on query complexity. For simple questions, it might use a lighter approach, while for complex queries, it could employ more sophisticated retrieval methods. Corrective RAG, or QRAG, incorporates self-evaluation mechanism that grade retrieval information for relevance. If it determines that the retrieved context isn't sufficient, it will seek additional information to ensure accuracy. Self-RAG features autonomous generation for retrieval queries during response creation. The model identifies its own information gaps and refines searches iteratively, almost like having a conversation with itself to improve the answer. Agentic RAG implements agent-like behavior with document agents assigned to individual documents and a meta-agent orchestrating their interactions. This enables sophisticated synthesis of information from multiple sources, almost like having a team of searchers working together. AutoRAG. AutoRAG is an approach that automates the optimization of RAG systems rather than manually tuning parameters. AutoRAG automatically selects optimal retrieval strategies based on query types through a multi-turn dialog between LLM and the retriever, enhancing relevance and reducing noise in retrieved data. Dynamically adjust parameters like chunk size and retrieval depth. Use feedback loops to improve documents indexing and retrieval relevance. reduces manual tuning, making RAG systems more adaptable, implements self-evaluation to identify and correct hallucinations. The automation is particularly valuable in production environments where efficiency and adaptation are critical. Graph RAG. Very important and very popular RAG actually, but graph RAG represents one of the most sophisticated approaches, organized knowledge in a graph structure rather than in isolated chunks. This means information is represented as nodes, entities, and edges and relationships. Semantic connections between documents and concepts are captured. Retrieval becomes more nuanced based on contextual relationships. Complex queries required multi-hop reasoning and handled better. Hierarchical information and domain-specific structures are preserved. It can integrate with knowledge graph for enhanced reasoning. Imagine asking about the impact of policy change on a specific department. GraphRag can navigate the relationships between policies, departments, and impacts to provide a comprehensive answer. Here's a diagram of how it works. Actually, we probably all know what a graph is exactly. So the point of GraphRag is just extraction of entities and relationships and storing them properly in a data store so that later we can query and get very narrow and exact matching information on the query. GraphRag is ideal when you need to query and reason over interconnected graph structured data. For example, a citation network or knowledge graph. Example user query, let's see. Who are the top 5 researchers that Dr. Emma Garcia has collaborated with most frequently in our citation network? So in this case, GraphRag can find connections and depending on these connections, just find proper information. So now let's dive into what I consider one of the most valuable parts of this presentation, practical optimization techniques for RAG systems. While basic RAG implementation can be impressive, the difference between an adequate RAG system and an exceptional one lies in optimization. We'll explore several key optimization areas, how to process queries more effectively, mechanisms to improve retrieval accuracy, strategies for better generation, and frameworks to evaluate and continuously improve your system. This optimization can dramatically improve the quality of responses while potentially reducing costs. The first step in any RAG system is processing the user's query, and there are several techniques to make this more effective. Query expansion as related items to improve recall. For example, if someone searches for heart attack, we might expand this to include myocardial infarction. Query decomposition breaks complex queries into manageable sub-queries. If someone talks about comparing two different technologies of multiple dimensions, we might break these into separate queries for each comparison point. Hypothetically, document embedding asks what would the ideal document contain and search based on that representation. Query rewriting uses LLM to reformulate queries for better retrieval. For instance, turning who was the guy who painted the ceiling on the chapel in Italy into who painted the ceiling of the Sistine Chapel. These techniques can significantly improve what your system retrieves, leading to better answers. Once we process the query, we need to retrieve relevant information. Hybrid search combines semantic search, meaning-based, with keyword search, exact matches, to get the best of both worlds. Re-rank implements a two-stage approach. First, casting a wide net to retrieve potential matches, then applying a more sophisticated but computationally intensive model to rank the most relevant ones at the top. Rescoring is a type of re-ranking. Another powerful technique worth mentioning. It allows us to take our initial retrieval results and apply additional scoring factors beyond vector similarity, such as freshness, popularity metrics, or business rules to fine-tune the final ranking. This helps balance semantic relevance with other priorities that matters for your specific use case. A single vector works well for short production descriptions. Let's say like the iPhone 13 features a 6.1-inch display, a 15 chip, and dual camera systems. News headlines like stock market research at record high on Tuesday, simple question and answer pairs like what is the capital of France, Paris, you know. But what if the documents are huge and out of context? Or we want to have granularity and find just specific sections. Here's where multi-vector retrieval comes in, representing documents with multiple embeddings rather than just one, capturing different aspects of sections of the documents. Think about a huge book, a long research paper, or large technical documentation. Here's where chunking comes into play. In practice, I've seen hybrid boost reliability, but 15 or 15 feet 20% over just pure vector search in many domain-specific applications. Before I move on, I want to share with you that my colleague Sergey Nikolaev has a presentation on vector quantization techniques that we implemented in Mantocore search. I highly recommend checking it out if you're interested in optimizing the storage and computational requirements of your vector search systems while maintaining retrieval quality. Now let's talk about chunking challenges. When you want to split something really huge to be able to flexibly search for some terms in big documents or maybe some structured data. How you divide the document for storage and retrieval can make a huge difference. So strategic chunking is about finding the sweet spot in size and overlap. When chunks are too small, you lose vital context. When they're too large, your retrieval becomes fuzzy and imprecise. I've seen projects where simply adjusting chunk size improved answer quality by 30%. Semantic chunking breaks documents at natural meaning boundaries rather than arbitrary token counts. This keeps related concepts together, like ensuring a complete explanation of procedure stays intact rather than getting split mid-though. Hierarchically, chunking preserves your document's original structure. This means the system knows that the paragraph belongs to a specific section, which belongs to a specific chapter, maintaining the organizational logic of your content. Parent-child relationships connect relative chunks, helping the system understand that certain pieces of information, though separated, come from the same source document. This provides crucial context during retrieval. In my experience, the right chunking strategy can improve response quality more than almost any other single optimization, often delivering better results than even expensive model upgrades. The quality of your vector representations is crucial. Consider fine-tuning versus off-the-shelf embedding model. General models like OpenAI embeddings work well for many cases, but fine-tuning on your specific domain can yield significant improvements. Domain-specific embedding training can help capture nuances in specialized fields like medicine or law. Aware of embedding context limitation, most embedding models have maximum token limit that affect how you process longer text. Advanced pooling techniques for documents representation can improve how information is aggregated into single vector. A well-chosen embedding strategy can dramatically improve retrieval quality, which flows through a better final responses. Once you retrieve relevant information, how you present it to the LLM matters. Context-aware prompting techniques guide the LLM in using the retrieve information effectively. Structured prompts organize information in ways that help the LLM understand what's more important. Citation and attribution mechanisms encourage the LLM to reference sources, improving transparency and trustworthiness. Chain of thought and reasoning approaches guide the LLM to a logical process of using the retrieval information to formulate an answer. The difference between dumping retrieval context into prompt and structurally guiding the LLM can be difference between a confused, rambling response and clear, accurate one. To improve your RAG, you need to measure performance effectively. Beyond simple accuracy, consider comprehensive evaluation metric that assess different aspects of response quality, like specific benchmarks like RAGAS evaluate retrieval query quality, answer relevance, groundedness, and other specific concerns. Human evaluation frameworks provide qualitative insights that automated metrics might miss, and this can be partially automated for efficiency. Continuous evaluation pipelines allow you to monitor performance over time and catch regressions early. Remember, what gets measured gets improved, so choosing the right metrics is crucial for ongoing optimization. Don't overlook the value of metadata in your RAG system. Enhancing retrieval with structured information like document type, date, author, or department can significantly improve relevance. Filtering and routing strategies using metadata can direct queries to the most appropriate knowledge sources. Time-aware and recency-based retrieval can prioritize newer information when appropriate. Entity-based indexing and retrieval can improve precision when queries focus on specific people, organizations, or concepts. Metadata provides context beyond the text content itself, and leveraging it effectively can lead to more precise retrieval and better answers. To help you implement these optimizations, here's prioritized checklist approach. Start with basic query processing and chunking strategies before moving to more advanced techniques. Consider this effort versus impact matrix for optimization decisions. For example, implementing hybrid search typically offers high impact for moderate effort, while fine-tuning custom embeddings requires more resources but might yield less immediate improvement. For each optimization area, there are recommended tools and libraries that can save you implementation time. And finally, a suggested timeline for implementation phases. Don't try to do everything at once. Build a solid foundation and improve iteratively. Remember, the RAG optimization is a journey, not a destination. Start with the basics, measure your progress, and continuously refine your approach. Now let's talk about our own implementation journey at Mantocore Search. We made a search across of our website and manual with AI on board. You can check at mantocoresearch.com how it works, but before, let's talk about us. We are building a full text search database and vector search database offering high performance search capabilities. Our system is designed to be extremely efficient and fast, handling complex queries with minimal resource usage. Mantocore Search is a fast and flexible open source database for search with many customizations and tuning options available. You can run an instance even on 1 core and 1 gigabyte and enjoy fast performance. And importantly, Mantocore Search written in C++ for performance and fully open source, but allowing for customization to specific use cases. You know, developing in C++ can be time consuming, and that's why we make it possible to write some modules not only in C++, but in PHP too. Yeah, PHP, and expand the functionality of database is just like really easy. So in some cases, it helps you not to move some logic to your application level and simplify things, or allows you to get more from the database solution we offer. This combination of text and vector search capabilities make Mantocore particularly well suited for RAG implementations. Besides working on Mantocore Search, we are also doing some open source things that can simplify the life of developers and be useful for automation. I want to tell you more about what you're building also. One of these tools is CLT, Command Line Tester, which simplifies the testing approach. Simply write some bash commands and expected outputs, lock it, test it, and make sure you do not break things when you push new changes in your project. It's written in Rust for performance and can run your test in any image you provide, I mean Docker image. We also have reusable GitHub action for simple integration in CI. We use it to cover integrations test almost everywhere. Another tool is Auto-Translate, powers automatic translation on our website and documentation. It's simply a CLI tool that smart enough to translate with AI and validate that the translation is not broken. You know, AI sometimes corrupts files and response is not what you really expect. So we implemented some protection techniques that validate that files and more likely preserved translation one same original without any mess provided. So smart translation only blocks those changes that really needed because when you change something in file, we can translate only that part, and that's all. It's still early, but we plan to add it. GitHub action also you can check. And same word for GitHub workflow automatically tags each commit without having anything about what version you are working on. You push to the repo and forget about versioning. The GitHub action does it for you just by analyzing all commits you pushed and automatically incrementing versions for the last tag version. Let's say you just following GitHub conventions and put like fix feature or whatever in commit, and this is how the tool understands when to increment. Okay, feel free to learn more and check those tools in our repository on GitHub. But now let's move on. So now let's go back to our journey and talk about our real-world implementation at Mantocore Search. This is how our web search implementation looks. Just an iframe showing results which can be easily integrated into the website. You can take a look. We recently tackled the challenge of improving search on our website, mantocore.com. We wanted to make it faster and more useful for our users to find exactly what they're looking for. Since we're making search technology, it made perfect sense to use our own tools for this job. An interesting decision we made was to crawl our site HTML rather than using the markdown sources directly. While we had access to the raw MD files, we wanted a solution that could be controlled from a single place and reflect exactly what users see on the live site. This approach allowed us to leverage both the keyword search and vector search capabilities that Mantocore offers, which ultimately proved crucial for our implementation. The first major challenge we encountered was figuring out how to split content into meaningful chunks. This might sound simple, but it's actually one of the trickiest parts of building an effective RAG system. We experimented with different approaches before settling on a header-based chunking strategy, thanks to HTML and DOM being well structured, with fallback to a size-defined chunking approach when we have an unstructured page. Not every page is like perfect. Sometimes we have no headers there, so what to do? This preserved the logic structure of our documentation while ensuring chunks weren't too large. We also discovered that adding the page title to each chunk before generating embeddings significantly improved context and relevance. Our format became something like title, getting started with Mantocore, and content installation step guide. When we tried to check the results of the search, we also noticed some weird issues with the relevance. We wrote scripts to measure cosine similarity on our actual queries and found surprising variations across providers even with identical data. For embedding, we tested multiple providers, including Google, Voyage, and Gina. And here's important lessons. Benchmarks aren't always the best starting point. Different embedding models perform very differently depending on your specific data and database. If you can always prefer to use domain-tuned embeddings. So this is the point. If you have and you starting to do something, start with domain-specific embedding because it will provide much better quality, Oh, okay. Once we had our search working, we faced another challenge. Our chunks were quite large, and when user got result, they needed to see exactly which part was relevant to their query. We could have used AI to extract the most relevant parts, but that would be slow and expensive at scale, Instead, we came up with simpler solution that worked brilliantly. We split each chunk into individual sentences, generated embeddings for each sentences, and then for any search result, we could identify and highlight the most semantically relevant sentence from that page. This is dramatically improved the user experience with minimal computational overhead. And thanks to browsing standards, we could use, like the text equals fragment identifier to land user directly to the highlighted text when they click it on result link. This small feature made a huge difference in usability. Well, this is how it looks. This is how the browser support text for the landing thing looks. The good thing here is that we could not do anything and reinvent the wheel, just follow browser standards, use what already you can use. A little effort, but already working. So integrating the search with AI to create a full RAG system was our next challenge. We started with simplest approach, perform vector search and feed the results as context to the AI. But we quickly found that providing too much data sometimes confused the model. The lesson here was clear. Your goal with RAG is to narrow context as much as possible, not to provide everything to model. When we found that vector search alone wasn't always delivering quality results, we implemented a hybrid approach. We exposed two search functions to the AI, keyword search and vector search, and let AI decide when to use each one. This allowed the AI to extract meanings from user inputs and gather better context on its own. But we hit another challenge. When we removed initial context entirely, they are sometimes struggled to use the tools properly, even when explicitly instructed to do so in prompt. It would respond this "I don't know" rather than trying to search for information. So our solution was a hybrid approach. Provide minimal but essential initial context. We come with like 3 pieces of documents, plus expose search tools that AI can use to gather additional information when needed. And about tools, I mean like keyword search and vector search. So if AI is missing some context from what we gave, it can call tools and get more information. This balanced approach dramatically improved the quality and relevance of responses. Okay, here the final flow of how it works on the UI with the user request response. Let's look. First, when the user types and sends something by pressing enter, we get context from our RAG. If the user does not click enter, we perform just a type as you search function. Once we get something related, usually just 3 documents, we send a prompt to the LLM and give it the possibility to call tools to do extra searches in case LLM can refine queries and get more information when context is missing or just need something more, The LLM can call and get more context or just respond to the user to the questions if it has all the required context for it. And here, how we finished our architecture to utilize RAG while indexing data for retrieval with LLM. So first things first, we get the URL to start, read it, and go through the DOM by trying to find all other links, and that will be processed in parallel. We also get meaningful context without headers and footers and split it in by structured HTML output chunks for each header related. What I want to say, we just try to get all information using DOM and native methods from each page and chunking, but like headers when it's possible, or fall back to chunk by size. So once we get all chunks, we batch them and also split each chunk separately into sentences. Once we reach a certain amount of batches to process, we send a single request to the API to generate embeddings and store all we collected. Yet, simple but still powerful, preparing a pipeline that can utilize parallelism and generate embeddings in batches instead of sending each request individually and losing time on HTTP latency. Through our implementation journey, we discovered several critical insights that can benefit anyone working with retrieval augmented generation. systems. First, chunk size is fundamentally important. Excessively small chunks yield random, irrelevant results, while overlay large chunks and cause the AI to overlook crucial details. Finding the optimal balance is essential. For human-oriented responses, we found that the ideal chunk should typically consist 1-2 coherent paragraphs sharing the same context and meaning. Second, embedding quality varies significantly across providers and applications. Rather than defaulting to popular options, it's advisable to evaluate different embedding against your specific data and queries. While domain-specific embedding models generally deliver superior results, even when working with general-purpose models, testing multiple providers is valuable as performance can vary substantially across different datasets. The key takeaway is that optimal solutions are highly case-specific. Don't hesitate to conduct thorough testing before making implementation decisions. Third, when providing context to AI, less is often more. Your goal should be narrow down the most relevant information, not to overwhelm the model with everything you have. So more you give, more distracted AI becomes. So remember this. Fourth, highlighting is crucial for user experience. By splitting chunks into sentences and identifying the most relevant ones, you can guide user directly to information, the information they need. If you store like huge amount of chunk in your database and you just query it by vector embedding, you also need to highlight exactly what user looking. Otherwise, you need to show very big chunk or keep small chunk, but small chunk yields to bad results. Remember this. Finally, hybrid approach that combines initial context with the ability to search for more information give the best results. It provides the AI with starting point while allowing it to gather additional context when needed. We've deployed this system on our website, and while we consider it just the beginning of our journey, it's already delivering great results. We are storing everything in Mantocore, which gives us excellent performance, and we are continuously refining our approach based on user feedback. Our next step is to integrate auto-RAG capabilities directly into Mantocore search based on what we learned, making it easier for others to implement these techniques from the box. We'd love to hear your ideas and feedback as we continue this journey. Still early. Well, all right. So that's wraps thing up. Thanks so much for sticking with me through this deep dive into RAG systems. I really hope you found something useful in our journey, whether it's the optimization techniques we covered or some of lessons learned from our implementation and Mantocore search. Trust me, we learned plenty along the way. I'd love to hear your thoughts or answers and questions you might have. Maybe you're facing similar challenges in your RAG implementations, or perhaps you're curious about specific optimization approaches we've tried. Don't be shy. Feel free to reach out to me directly at Dmitrii@mantocoresearch.com if something comes to mind later. And of course, you can check our mantocoresearch.com for more details or what we are doing in this space. Okay, thank you guys.